Hubble's law. So what governs how things happen in the universe at great distances, large distance scales, large time scales, talking about processes that have been happening since the universe was created, essentially, since the Big Bang. So interesting topic, I think. Very fun topic. All right, so what's here? So we're moving out to our distance scale, and today we're going to deal with kind of the top of our distance ladder. We're going to learn how to measure out to the farthest reaches, the edges of the universe. We're going to do that using a topic that you guys already are pretty familiar with. Hopefully, are very familiar with if you finished Lab 7 or just done something in Lab 7, which is concept of redshift. So topics: Hubble's law of the obvious place in the universe. We're going to learn about the Big Bang and about it not being an explosion in space, but of space itself. Matter, energy, planets, galaxies, stuff in the universe was not doing the exploding, doing the moving, but the actual fabric of space was moving. We'll talk about that. We're going to determine where the center, if there is, of the universe is at, or whether or not there's a center to the universe, and what the rate of expansion of the universe is. Okay, so as the universe started with the Big Bang, is it continuing to expand at an accelerating rate? Is it expanding at a relatively constant rate? Is it decelerating? Is it starting to slow down and possibly move toward what some people theorize is a big crunch, so it will actually get to a point where it stops expanding and starts collapsing again on itself? I'm not going to go too deep into those last topics, but we'll explore the nature of our universe expansion. Okay, so Hubble's law. So in Hubble's law, in Lab 5 we use nearby variable stars to measure distances to nearby galaxies. Separated variable stars, we use them to measure distances to nearby galaxies, and we use type 1a supernova to measure to faraway galaxies. Okay, supernova are very bright events, so we can see further out in space and use that as a standard panel distance measuring tool. In Lab 7, we talked about redshift. And what does redshift tell us about an object? You notice a change in wavelength that corresponds to a relative difference in what that object relative to us is. Velocity, exactly. So if we notice a redshift of some emission, we know that there's a relative speed, difference in speed or difference in velocity between us as the observers and that object out in space. And so the basic idea here is that redshift is proportional to velocity. And so in this lab, we're also going to be using the concept of redshift. So we're going to look at how redshifted or blue shifted some emission is as a measure of how fast toward or away from us an object is moving. Again, just a reminder, redshift is proportional to the difference in the observed minus the emitted wavelength over the emitted wavelength. And in this case, we're just going to be concerned with the redshift value, which we're denoting by z. Okay, so you see z in this lab, it's just a shorthand for redshift. It's the part that doesn't depend on the speed of the emission. Velocity is equal to c times z, c being the speed of light, z just being how redshift is. When Hubble looked out across the universe and measured the redshifts of various galaxies, he found a pretty consistent trend. The farther away something is, the faster it appears to be moving away from us. Okay, so things nearby are moving away from us at some speed, and if you look at something that's much farther away, it's moving away much faster. So there's a corresponding trend there. And if you take that view, and everything is expanding away from us, the further away you go, the faster way it's moving, and you take that entire picture and you run it backwards in time, you come to the concept of the origin of the Big Bang, that everything exploded from a single location approximately 13.7 billion years ago. Okay, so there are some problems with this. If we look at these galaxies and we measure redshifts, that leads us to believe that they're moving away with some recessional velocity. But what that means then is that everything in space originated from a central location via the Big Bang and expanded outward. But there's some problems with this viewpoint. For example, what do you notice if you take a pebble and you throw it into a pond? What results? You just did it and you mounted ripples. Okay? So you see little waves moving outward from that central location on the surface of that pond, on the surface of the water. And if you look at that in a three-dimensional view, if something exploded from a central location, you would say the same thing. You'd see basically ripples, except in this case, it's in three dimensions, so it's spherical shells. you'd see expanding shells of matter moving out from that central location of the explosion. But when we look out into space, that's not what we see. This is 2 slices of some galactic sky survey. So we looked out between these 2 regions of space, and we measured a bunch of galaxies, or observed a bunch of galaxies. And this is what we found. So each one of these little points, little blue dots that make up these strands, is a different galaxy. And so what do you notice about this? There's no shells, right? There's no ripples, there's no concentric lines of matter. What we'd expect if there was a central location of an explosion and everything moved out from that location. What we see is that everything is distributed isotropically and homogeneously. What that essentially means is that in every direction that we look, we see the same collection, the same amount of matter, and at each location we see the same amount of matter. So you don't really see that there's an expanding shell. Yeah, there's a clump here, but that's probably just an effect locally due to gravity. It's not a big picture effect. And then the other thing you might notice is that it gets fainter out here. And that's not because there's less matter there, it's just because we have an observational bias. We have a harder time observing out at great distances. But we expect that there is an equal amount of matter distributed throughout the universe in every direction that we look. Okay, so our understanding of this kind of big explosion of matter and energy from a central location is getting a little bit debunked. Okay, we don't see what we expect to see. There's another big problem with this view of the Big Bang, which is that when we look out into the universe and we measure redshifts, we find values greater than 1. So this is a Hubble deep field survey, and they have highlighted various redshift values just taken by looking at the energy, just like you did in Lab 7, looking at some mission. And we find values that are greater than 1, which tells us what about the velocity with which those objects are moving. Okay. Faster than the speed of light. The velocity, processional velocity is equal to c, the speed of light, times the redshift. So if the redshift is greater than 1, that means the speed with which they're moving is greater than the speed of light. That's a big no-no. It's a big problem. Right? No matter in the universe can move in vacuum faster than the speed of light. There's some caveats to that, but it's not anything we're going to get into. So there's something going on here. We're not actually measuring true Doppler redshifts like we expect. There has to be an explanation for this. So we go back to our boss man, Einstein. Some other things that he figured out was that while light or anything sort of tangible in the universe cannot move faster than the speed of light through space, space itself has no limit on the speed with which it can move. So if we think about the universe being the surface of a balloon, and we were to blow up that balloon, all these objects, right here, it's coins on the surface of the balloon, right, would be expanding away from each other. And so that's actually what we're seeing. The universe is expanding. The space in between all these galaxies is expanding. And so these galaxies are being pulled along with it. It's not that they're moving faster than the speed of light. It's that the universe is actually expanding faster than the speed of light. So there's a big endpoint. Consequently, the Big Bang is better described not as an explosion in space, but as an explosion of space itself. The actual fabric of space is what is doing the expansion. So then, if that's true, why are we seeing these redshifts? Nothing. It's just space that's expanding, and these things aren't actually moving at different speeds. And why are we seeing redshifts? Well, it turns out that light doesn't work like normal matter. Earth is bound together by gravity. Our solar system is bound together by gravity. Our galaxy is even bound together by gravity. And our local group of galaxies is likely bound and clumped together by galaxy, or by gravity. But if you think about the space in between that, there's nothing keeping that together. And it turns out that light has nothing keeping it together. It doesn't have gravity to keep it together. It has no what's called internal cohesion. So as space expands, light expands with it. And so if you think about a light wave riding on this fabric of space, as that fabric is expanding, so are those light waves expanding. So another way we can think about Hubble's law is that the farther away something is, the greater its redshift is. And in this case, we're thinking about redshift instead of recessional velocity because we're not actually moving at that speed. We call this redshift cosmological redshift. So the big difference here is that the light is being redshifted by the expansion of space and not actually by a recessional velocity or by a Doppler effect. So the key here is that if we can measure a redshift, we can correlate that with the distance. And presumably, with this Hubble deep field, we can measure redshifts for really, really far away objects. So we can measure out to very far distances, and that's why on our march out into space, Hubble's law sits as the top of our sort of distance scale. The furthest object in space was found in 2005 by Dr. Reicher and his group using this exact thing, cosmological redshift. It's a gamma ray burst. Very, very bright, very, very energetic object. At that point, it was measured at a redshift of over 6. It correlates with a speed of greater than 600% of the speed of light. Obviously, it's not actually moving that fast, but that's the effect of something being emitted a long time ago, being very far away. So it's kind of one of the things that you need to keep in your head is that distance and time on universal scales are correlated. The further something away it is, the further back in time you're actually looking when you receive that light. So it's going to take some getting used to. It's something you're going to have to think about when you actually do some thoughts and answer some questions in this lab. Just think about that distance and time are correlated. Okay, so that was the background. Take a deep breath. Get on to the actual procedure. The procedure is pretty quick. The measurements that you're going to take don't take very long. Any questions before we get into the actual method? Lab method. Okay, so how are we going to do this? Well, we're not going to measure a bunch of redshifts of receiving galaxies in a Hubble survey. We're going to create our own little universes with rubber bands. Okay, so the idea here is to approximate the expansion of the universe with an elastic source, a rubber band. We're going to mark some theoretical galaxies on it, and we're going to expand the universe in time. Use your imagination on this one a little bit. I'm not going to go too deep into the actual setup. It's pretty straightforward. You mark 5 dots on the rubber band. Those are your 5 galaxies. And you're going to measure between, first section, you're going to measure between the distance between the first one and each of the other ones as you expand that rubber band to greater and greater distances. On a practical point, be sure to anchor your tack opposing the pull of the rubber band. So if this is my setup, I'll just show this. So if I'm going to be pulling rubber band in this direction, I have the tack anchored so that it's opposing that pull. Point being that these things rip out of this little pegboard and go flying across the room and hit some of the diagram, feel pretty bad. And so will they. So whenever you do this, just make the tacks pointing into it rubber band. If you want to bring your little setup to the edge of your table, you can actually go through the bottom. Just be careful because these things aren't that thick, so you'll work out the other side. Don't yourself, don't work each other's eyes out. Your rubber bands will break, presumably some of you, but there's extras, so don't worry about it. It shouldn't affect your results. Okay, so what are we going to do? We're going to take our theoretical universe and we're going to expand Galaxy 5 at a rate of 3 centimeters per minute. Per minute, you're just going to do it, measure it, and do it, and you're going to record the distance between Galaxy 1 and each of the other galaxies for a Galaxy 5 distance as shown here. Okay, so the basic idea is that you're approximating like a Big Bang, pretending like the universe started with everything in one spot and then expanding at 3 centimeters per minute and measuring the distance as it stretches. All right, so once you record all those values, the 2 things you're going to want to know, well, you'll be asked to plot them, but the 2 things you're going to be interested in is the light travel distance. Okay, so how we need to know a distance measure, right? Because we want to replicate Hubble's law, so we need to know a redshift versus a distance. And the actual distance, the coordinate distance, is dependent on d then, which is the distance between galaxy 1 and the other galaxies when that galaxy emitted the light that we're just now receiving. So read over that a couple times. But the basic idea is that if the current time now is when galaxy 5 is 27 centimeters away, when it actually emitted the light that we're now receiving, it was only 15 centimeters away. Because it takes time for that light to travel to us at galaxy 1. Okay, so D then, they just highlighted for you, is this yellow, or all these yellow boxes. And presumably D now is the distance that it is now, so that's just the last row in your table. Basically, the distance that the light traveled is some average distance between these two. So if you look down, they just tell you that the distance is approximately equal to the average of then D then and D now. What we're actually interested in is a luminosity distance. So remember with our standard candles, depending on what the observing conditions were, that correlated with how far away it's, the brightness of something. So this is like brightness, apparent magnitude versus luminosity, absolute magnitude. That helps us determine a distance. And in this case, what we're measuring is not it's a coordinate distance, not a luminosity distance. So in order to get the value that we're actually interested in, luminosity distance, we have to apply a correction factor, multiply by a correction factor, which is just given here. It's a ratio of the distance now over the distance then. It's a pretty basic calculation. Once you take your measurements, you then fill out this table, and that will allow you to figure out the cosmological redshift. So redshift is based on what? It's based on change in wavelength, right? So if a redshift is equal to a change in wavelength over the wavelength emitted, or wavelength then, we just find out that that's proportional to the distance. And so you can just solve and cancel out the proportionality constant, and we get that the redshift is equal to the difference between the distance now and the distance then over the distance then. So it's kind of the same thing, just replace emitted wavelength distance then and observed wavelength distance then. Okay, so you make your observations, and you basically copy these down from your table, and make two sets of calculations, and now you have a measure of redshift versus distance. So we just replicated Hubble's law. One thing I do want to note, there's a lot of graphs, a lot of plots that you're going to be asked to create and submit in this lab. Please be careful about your title and axes. Figure 1, beginning with time equals 0, plot distance between versus time. What should your title be? Distance between galaxy 1 and 5 versus time. Okay. Whatever it asks you to plot, that is your title. In this case, it tells you what should be on the y and on the x-axis. So be careful with that. Okay. More than half of the points for each of your plots is going to be, did you title it and label the axes correctly with units? If you forget that stuff on 10 plots, it's a lot of points. So you're going to be asked to overlay a couple plots on top of one another. It'll ask you to plot like one set of data, and it'll say, now plot overplot your data from part B or whatever on top of this. It's basically asking you to compare I think accelerating or decelerating versus the constant expansion. And so that's just, when you're in your plotting tool, you go to the dual option. And then you'll get 2 lines instead of 1. So you're going to have a first set of x and y, and then a second set of x. So then, once you do that first time through, then you're going to ask you to do the same thing, except from the Galaxy 2's perspective. So this is basically allowing you to determine, is there a center of the universe? Right? So if you found one thing, if you found that everything was moving away at a constant rate from you at Galaxy 1, you might think that you're in the center of the universe, right? But if you then go to Galaxy 2, you make the same measurements, and you find the exact same thing, then that probably means that Galaxy 2 could then say that they're the center of the universe, right? So the end result of that is that there is really no center. Everything's expanding away from everything else. And that's the idea that you're supposed to get to. The final 2 sections, you're going to be doing the expansion measured from Galaxy 1 at an accelerating and decelerating rate. So same measurements, just the distance to which you're pulling Galaxy 5 is slightly less or slightly more than it was before. Decelerating, accelerating expansion. And that's the lab. Again, data tables are pretty quick, but there's a lot of graphs, so you got to be careful with that stuff. The final question you're going to be asked, this graphic sometimes confuses people. So they give you 3 curves here. The middle one they label as constant rate of expansion. You're going to need to identify which of these other two curves is accelerating and decelerating rates of expansion. And the black points are actual observations. So, do the black points, which of the curves do these dots follow most closely, basically, is what it's asking. I think that is all I have to say.